Have you ever stopped to think that a glass of milk, liquid, heavy, and highly perishable, can cross oceans, sit in storage for months, and come back to life with just a little water? It sounds like a laboratory trick, but it's pure industry. Inside a factory, tons of fresh milk flow into steel pipes, pass through heat, vacuum, filters, massive towers, and streams of hot air until they become a fine, pale powder that is surprisingly stable. And here's the fascinating part. The factory isn't actually turning the milk into something else. It removes nearly all the water, preserves the milk solids, and creates a product that can travel far greater distances than regular milk. A droplet becomes mist, the mist becomes a particle, and the particle falls like dry rain inside a metal tower, taller than many buildings. Welcome to Factories and Facts. Today you'll discover how tons of fresh milk enter the factory, pass through heat, vacuum, pressure, and an astonishing drying tower, until they become that pale, seemingly simple powder that can travel for months before becoming milk again in your glass. If you watched our previous episode, you saw how bees transform nectar into honey. No motors, no control panels, just thousands of bees working inside a living factory. Now, almost the opposite happens. Milk leaves the farm fresh and enters a factory filled with massive machines, heat, and vacuum to become a powder that lasts for months. And before we continue, make sure you're subscribed to Factories and Facts, because today we're answering one of those questions that sticks in your mind. How can a fresh food straight from the cow and so easy to spoil become a powder that lasts for months and can still turn back into milk in your glass? You're about to discover that this transformation is only possible because of one of the most precise operations in the food industry. It all begins long before the drying tower. Milk leaves the farms in insulated tanker trucks, kept chilled to slow the growth of microorganisms and preserve its quality. When it reaches the processing plant, it doesn't go straight into production. First, it goes through a series of tests. Technicians check temperature, acidity, fat content, unwanted residues, density, and overall quality. One bad batch can compromise thousands of gallons, so the factory entrance operates like a tightly controlled checkpoint. Once approved, the milk moves through sealed pipelines, completely isolated from the surrounding environment. This is one of the most invisible parts of the process when you look at the finished product. There are no open buckets and no milk sitting in makeshift tanks. Pumps, sensors, valves, and digital control panels manage the entire flow. In large processing plants, the milk seems to move through a metallic city, with stainless steel highways carrying the raw material from one stage to the next. At this point, the factory has to make an important decision. What kind of powdered milk will it produce? Whole milk powder retains much of the milk's natural fat. Skim milk powder goes through a separation process to reduce that fat. That decision changes the flavor, application, stability, and final market. A plant may produce powder for household use, chocolate, cookies, ice cream, baking, formulas, and many other products. The remarkable detail is that most of milk is water. So making powdered milk is, above all, a battle against moisture. But the industry can't simply boil everything in one giant vat, because too much heat changes the flavor, color, proteins, and solubility. The secret is removing the water efficiently without damaging the milk's most sensitive components. After receiving and standardizing the milk, the next step is pasteurization. The milk is heated for a carefully controlled amount of time to reduce microorganisms and make the process safer. Then it is prepared for the stage that completely changes the game: concentration. Up to this point, it still looks like milk. After that, it begins to behave like a thicker liquid, almost like a dairy syrup, ready to enter the heart of the factory. And here's the key detail. Powdered milk doesn't begin as powder. It begins as concentrated milk. The factory first removes a large portion of the water in evaporators using heat and vacuum, before sending the product to the final drying stage. Without this step, the drying tower would consume far more energy and operate much less efficiently. Imagine a series of enormous cylinders working like industrial lungs. The milk enters thin and fluid. Little by little, it loses water in the form of vapor. Because the system operates under vacuum, evaporation happens at gentler temperatures than it would under normal pressure. That helps protect flavor and quality while also saving energy. Inside these evaporators, nothing is left to chance. The milk forms thin films along heated surfaces or flows through patterns designed to maximize contact area. The more the liquid spreads out, the more easily the water escapes. Vapor produced in one stage can be used to heat the next, creating an intelligent cycle of energy recovery. It's almost like using one machine's breath to power the next. In some production lines, this concentration happens in multiple effects, a sequence of stages designed to make better use of steam and reduce wasted energy. For the factory, every bit of energy saved here means lower costs, more predictable production, and less heat stress on the milk. At this stage, the texture changes. The milk stops looking like a beverage and becomes a concentrate. It grows more viscous, heavier, and richer in solids. The plant monitors total solids closely because too little concentration puts extra strain on the drying stage, while too much makes the product harder to pump. The goal is to find the exact point where it still flows through the pipes, but has already lost enough water to enter the tower efficiently. This is where a common misconception comes in. Many people imagine powdered milk as milk that has been scorched and scraped off some kind of hot surface. Older and more specialized processes using heated drums do exist, but the most widely used method for modern dairy powders is spray drying. In this process, the concentrated liquid is not spread across a surface and burned. It is broken into microscopic droplets inside a stream of heated air. Before the milk reaches that tower, however, the factory can still fine-tune the formulation. Protein, fat, lactose, and other components can be standardized depending on the final product. With whole milk powder, the fat requires extra attention because it affects flavor, aroma, and shelf life. With skim milk powder, the priorities shift. Solubility, color, performance in recipes, and response to heat become critical. And if you enjoy seeing the hidden side of factories, leave a like, because processes like this reveal just how much engineering, energy, precision, and control go into something as ordinary as milk. That simple powder inside the package is the result of a long chain of industrial decisions you'll never see on the label. Now the concentrate moves through filters and into feed tanks. It has to reach the drying tower under stable conditions. Temperature, pressure, viscosity, and flow rate all have to work together. If even one drifts out of range, the droplets can become too large, too small, too wet, or scorched on the surface. It's like fine-tuning a massive spray system where every droplet has to dry at exactly the right moment. Then comes the most cinematic moment in the entire process. At the top of the drying tower, the concentrated milk is atomized. Atomization means breaking the liquid into a mist of extremely fine droplets. This can be done with high-pressure nozzles or rapidly spinning rotary discs. The goal is to create an enormous contact area between the milk and the hot air. The smaller the droplet, the faster the water evaporates. Think of one wet towel folded up and another spread completely open on a clothesline. The open one dries faster because more of its surface is exposed to the air. Inside the tower, the same principle is pushed to the extreme. The milk stops being a thick stream and becomes a cloud. Each droplet carries milk solids and water. The moment it meets the hot air, the water evaporates almost instantly, while the solids form dry particles. Here's a detail that sounds almost contradictory. The air is hot, but the product doesn't necessarily cook the way many people imagine. As the water evaporates from each droplet, it absorbs much of the thermal energy, helping protect the particle itself. That's why spray drying, when carefully controlled, is considered a relatively gentle process for heat-sensitive ingredients. The tower is so tall because each droplet needs time in the air. It enters as mist, dries as it falls, or moves with the airflow, and reaches the bottom as powder. If it falls too quickly, it stays too moist. If it remains exposed too long or receives too much heat, quality can suffer. It's a carefully controlled choreography of gravity, airflow, temperature, and particle size. The operator doesn't stare inside the tower like someone watching a pot on the stove. The process is monitored on screens. Sensors track inlet and outlet air temperatures, pressure, moisture, flow rate, and overall system performance. Even small changes can affect the final powder. A batch intended for beverages needs to dissolve easily. A batch for chocolate has to blend correctly. A batch for baking needs to perform predictably in the dough. And here's something most people never realize. The powder leaving the first drying stage isn't always ready for packaging. Many factories use fluidized beds for a final stage of drying and cooling. The name sounds complicated, but the idea is easy to picture. Streams of air make the particles behave almost like a bubbling liquid. They remain suspended, keep moving, lose their remaining moisture, and cool to a safe temperature for storage. This stage helps prevent caking, improves stability, and prepares the powder for handling. Powder that is too hot inside the package can create condensation. Powder that is too moist can form clumps. Powder that is too fine can create excessive dust, make filling more difficult, and dissolve differently. That's why the factory searches for the exact point where every particle may look tiny, but carries an enormous amount of engineering behind it. And what about you? Did you think powdered milk wasn't real milk? Or had you ever stopped to think that it's the same fresh milk, just with almost all of the water removed? Tell me in the comments. After drying comes a step that can make the difference between an ordinary powder and one consumers actually enjoy using: Instantization. Many people have seen powdered milk form little clumps in water. That happens because very fine particles can get wet on the outside, stick together, and prevent water from reaching the inside. To improve dissolving, manufacturers can agglomerate the particles, creating larger, more porous granules. Think of it as turning fine dust into controlled clusters. Those agglomerates contain tiny spaces that allow water to penetrate more easily. The result is a powder that sinks, wets, and disperses more readily. In some products, small amounts of approved emulsifiers may also be used to improve reconstitution, especially when fat is present, because fat and water do not naturally blend well without some help. Next, the powdered milk passes through industrial sifters. They remove oversized clumps, make particle size more uniform, and prevent off-spec particles from moving farther down the line. Magnets and metal detectors may also be used to protect the process from metallic fragments. The level of control may seem excessive, but it makes sense. When a factory handles enormous volumes, one tiny defect can become a very large problem. The laboratory keeps monitoring the product throughout the process. Samples are collected to check moisture, fat, protein, acidity, solubility, scorched particles, microbiological levels, and other characteristics. Color matters too. Powdered milk that is darkened can indicate excessive heat treatment or unwanted reactions. An unusual odor can signal oxidation, especially in products that contain fat. Packaging is another critical chapter. Once powdered milk is finished, time is not its only enemy. Moisture, oxygen, heat, and light all matter. That is why many packages use barriers against water vapor and air. In cans or more protective packages, manufacturers may also reduce oxygen exposure to preserve flavor and slow fat oxidation. The goal is to keep the powder dry, free-flowing, and stable until the consumer opens it. Filling happens on high-speed machines with precise dosing. The powder drops into cans, pouches, or larger bags intended for food manufacturers. Scales verify the weight. Sealing machines close each package. Lot codes and expiration dates are printed for traceability. If a problem is discovered later, the company needs to know the exact day, production line, shift, and raw materials behind that product. That traceability is one of the most important and least noticed parts of the entire process. A package on a grocery store shelf may look anonymous, but it carries its own industrial identity. Behind one small code are records of suppliers, laboratory tests, temperatures, production times, operators, tanks, and equipment. That is how the supply chain can investigate irregularities and help protect consumers. There is also extensive cleaning between production runs. Dairy lines cannot be treated like ordinary piping. Clean-in-place systems circulate specially formulated cleaning solutions through tanks, valves, and pipes without requiring the entire system to be taken apart after every cycle. Then come rinsing, inspections, and final clearance. The goal is to remove organic residue that could support microbial growth or contaminate the next batch. Another common myth is that powdered milk lasts so long because it contains powerful preservatives. In reality, most of that protection comes from its very low moisture content. Without enough available water, many microorganisms struggle to grow. That does not make the product indestructible. If it is stored poorly, absorbs moisture, or is exposed to heat, it can cake, lose flavor, and decline in quality. That is why the instruction to keep the package tightly sealed really matters. Once the consumer leaves it open, the powder begins absorbing moisture from the surrounding air. That carefully dried product, protected all the way from the factory, suddenly starts battling the humidity in your kitchen. And in humid climates, that battle becomes even harder. Once packaged, the powdered milk moves into boxes, onto pallets, and out to distribution centers. And this is where its biggest advantage becomes clear. The reason this product spread around the world: transportation and storage. Liquid milk takes up more space, weighs more because of its water content, and in many cases requires refrigeration. Powder concentrates the nutrients into a smaller volume, making it easier to ship to distant locations, food assistance programs, manufacturers, and regions where keeping fresh milk is more difficult. But the journey still isn't over. Before reaching the market, some batches may remain in quarantine while final laboratory results are reviewed. Only after approval are they released for sale. To the consumer, it may look like the factory simply filled a package. To the industry, every package is the final result of a chain of decisions that began on the farm and ended with a dry, precisely measured, fully traceable product. In the end, the magic of powdered milk comes from a combination of simplicity and precision. Simplicity because the basic idea is to remove water. Precision because removing that water without destroying quality requires tight control of temperature, vacuum, pressure, atomization, airflow, moisture, packaging, and sanitation. An entire world of engineering is hidden inside a single spoonful. And powdered milk goes far beyond the glass. It is used in chocolate, bread, ice cream, instant coffee, and countless other manufactured foods because it is easier to transport, store, and use than liquid milk. Instead of shipping truckloads of water, many factories can receive a dry, standardized ingredient that is ready to be added in exactly the right amount to each recipe. And when you mix the powder with water at home, you are reversing part of what happened inside the factory. The industry removed water using evaporators and hot air. You put it back with a little water and a few stirs. Of course, reconstituted milk does not recreate every characteristic of the original fresh milk, but it shows how technology can turn perishability into convenience. The next time you look at a can or a package of powdered milk, remember the invisible tower behind it. Remember the refrigerated tanker trucks, the laboratory tests, the vacuum pulling away vapor, the white mist falling through a giant chamber, the sensors correcting tiny deviations, and the particles being cooled before traveling across the country. What seemed like a simple product is actually one of the food industry's smartest answers to an old problem: how to move milk farther, keep it longer, and reduce the logistical burden. The factory doesn't fight the nature of milk. It works with it, removes its most vulnerable element, the water, and creates an ingredient that can wait far longer than liquid milk ever could. If you made it this far, make sure you subscribe to Factories and Facts, because so many everyday products are hiding incredible processes behind them. And tell me in the comments, which stage surprised you the most? Vacuum evaporation, the drying tower, instantization, or quality control? After this video, even that simple package sitting in your kitchen will probably look a lot more complex. And if you think you've already seen everything, then you have no idea what we revealed in our last episode. It's already appearing on your screen. Click it. And come with me to uncover another hidden secret here on Factories and Facts. Take care. I'll see you there.